Hello everyone. So in this lecture we will study the second order differential equation from basics introduction, and then we will move on to the things on the later parts. Okay, so let us first look how the most general linear second order differential equation looks like. So the general form of a second order differential equation is p of x y double prime plus q of t y prime r of t y equal to g of t, where p, q, r, and g are all functions of t. If g of t equal to 0, then we say that the differential equation is homogeneous. Otherwise, the differential equation is non-homogeneous. That is fine. So most of our encounters will be when the functions p, q, and r, they are constants. So if they are constants, so I'll show how to find the solution of the differential equation. So before that, so since it is a second order, so there will be two linearly independent solutions of the differential equation. So suppose y1t and y2t be two linearly dependent solution of, say, this is star, then one can easily check that y of t, which is a linear combination of those two solutions, that is sum c1 y1 plus c2 y2, is also a solution. So we can say that if there are two linearly independent solutions and there is no initial condition, then there are infinitely many solutions. Okay, so this is one theory. So now let us check how to find those two solutions. So to finding solutions to the differential equation of this form, so first we will look into the homogeneous differential equation only. So suppose we have the following homogeneous differential equation: y double prime plus some constant y prime plus constant y equal to 0. This is a homogeneous. So you can see that I have not taken a here. I have taken deliberately a to be 1, because if it is homogeneous, if some a is there, I can divide it down. I can send this down, and since this side is 0, so it does not matter. So we will take the coefficient of y double prime to be 1. This we can take without loss of generality. So given any differential equation of this form, we can form the characteristic equation corresponding to this differential equation. So characteristic equation corresponding to differential equation second order which is also homogeneous, second order comma homogeneous, is given by r square plus b times r plus c to 0. Now this equation has two roots. Suppose the roots are r1 and r2. So what are the outcomes, possible outcomes of R1 and R2? So R1 and R2 can be real and distinct. R1 and R2, real and distinct. R1 and R2 can be complex conjugates. That is R1 equal to some A plus IB, R2 equal to C plus, sorry, it's complex conjugate, right? A minus IB, that is complex conjugate. Or they can be equal, R1 equal to R2 equal to R, real and equal. These are the three cases. So for each of these three cases, we have a particular solution, standard form of the solution. So for the first one, R1 not equal to R2 and real, then Y1 is e power R1t and Y2 is e power R2t. The second one, R1 A plus IB, R2 A minus IB, that is complex conjugates, then Y1 equal to e power AT cos BT and Y2 is e power AT sin BT. Next, if R1 equal to R2 equal to R, real and equal, then Y1 equal to e power RT and Y2 equal to T power R. So these are the standard solutions. We can check it by putting this Y1 and Y2 and you can check that they will satisfy the differential equation. But you can take this as standard forms. So let us just quickly go through an example. Suppose we have a differential equation y double prime minus 16y equal to 0. Then what will be the characteristic equation? R square minus 16. So R equal to plus minus 4. These are the roots. Both are real and distinct. So y1 of t equal to e power 40, y2 of t e power minus 40. Hence the general solution is given by y of t c1 e power 40 plus c2 e power minus 40. So we started with the most general form of the second order differential equation. We reduced it to the homogeneous case and constant coefficients. We found the characteristic equation. I told you the conditions uh, when the roots are real, complex, real and equal, what will be the solution, and we saw an example. Thank you.